June 4th, 2023. Reading about the differential equations and the study so far, started with the idea of trying to figure out a difference between what are the subfields of differential analysis and how it ends up in then dynamical modeling is the idea of that anything that's actually a real world thing and that you want to model it by any kind of equations at all to attach to it a model and so make a modeling of it, that then there's the interpretation to attach to that and otherwise to end up having that then for quantities for real things they become variables of numerical things. Started with the idea of the first there's the differential analysis, which is just methods in analysis. It's real analysis. There's the fundamental theorems of the integral and the calculus, and that these are most well known as of after Newton and Leibniz's invention of the calculus, and then later into the formalisms with Riemann and Riemann sums and these kinds of things. And this is vis-a-vis whatever else we would otherwise inherit from the antiquarian, like the quadrature, the mensuration, which is the computation of area, or similarly for the differential, there's the computing of the gradient and the tangent, and then where that intersects the line to describe the instantaneous rate of change of things. So there's function theory involved, and how originally kind of got framed was this idea of submersions, symmetries, and sheaves, where talking about topology in the sheaves, or about sheaves then bundles, about any kind of a collection of like the tangent lines to a continuous curve that are continuously interpolate across something, making a sheave or sheaf. That of course a sheaf is the idea that when you're harvesting wheat by hand, what you do is you take a bunch of wheat together and you kind of tie a string around it or a piece of straw, and then when you cut this wheat all together, you end up with a sheaf. Right, as later in the higher order topological ideas, the bundle, but the sheaf is this idea first, and then the symmetries got into the idea that these are these subfields of the analysis to affect things that get tractable. So it's kind of after calculus, after linear equations and ordinary differential equations, and then after kind of and just very 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 introductorily, only just scratching the surface, as it were, or shallowly, I guess you might say, that then there's usually introduction and definition of the partial differential equations. These then relating to things like computing the gradient, and when you want to find out steepest descent or maximum descent in the gradient, and for things like principal component analysis, which is kind of the opposite of the field, when you want to figure out what way to divide something into three different variables, say, or however many components, so that then the inputs are mostly all in these three variables. Between computing the gradient and things like steepest descent and principal component analysis, those are two key things about the methods analysis. Fine. And so that gets into, for dynamical methods, finding things. All right. So the idea then was after these sheaves, and there's these symmetries, and the idea of symmetries is, for example, in the algebraic groups, the ability to establish what's a symmetry, so you compute what's for one region, and then via symmetry, you can use that to extend to compute the other half automatically, or rather, as a matter of fact. And so then the idea of the submersions is that looking in the differential topology, it kind of restricts itself to various settings. It says, kind of like when you're looking at symmetries, you can apply to some kinds of setups or ansatz. You can apply some methods of these symmetries, calca of them, a variety of them, various of them, varia. And similarly with this differential geometry, there's some ways to rewrite the systems of equations of these differential systems as formulas about these submersions and immersions, which end up making models of them where it's in higher or lower dimensions, or correspondingly that it's possible to arrive at closed forms for some things, or otherwise to it's again a kind of a subfield because it doesn't necessarily represent a general means to compute with these things generally, but it does offer for some cases tractability in what otherwise would be intractable. That the idea is to get things sensible, that they're sensible at all and well defined and reflect the ansatz or the setup and reflect what they are in terms. And then fungible, meaning, and we have at least some way to describe how they relate in their relations fundamentally, in their topology, which is why the sheaves is still so relevant, because the topological in the neighborhoods and all that really defines all these things, whatever are dynamics about the standard, non-standard, the continuum dynamics, including just the mechanics that's defining the topology. That for then these varia and about these means and methods of making the fungible parts of the milieu, then is the ability to apply that to a wider region, saying that okay, now that becomes tractable when that becomes some regular or ruleo that makes a completeness or a completion, so that then you can apply to that as of in more than its local region, in more of its global region. And so the sensible and fungible and tractable ends up kind of the desiderata of methods that allow one to arrive at first that there's a certain correctness implied by sensibility, because it has to be treatable by logic and application of a mathematical model that holds, that is faithful in a sense of model theory. And then to be fungible is that via other means of relations to other objects in the fields, arithmetic, algebra, function theory, set and part theory, geometry, and this could be that those basically wrap up for topology, and then operator calculus over those are all the moving parts I really think about. Arithmetic and algebra, function theory, geometry, and topology and operator calculus. And then that set and part theory are basically for descriptive axiomatics and models the same, and when everything's one pure theory. Right? So that then as these fields and the methods, and then for the sensible and what's the fungible in terms of that then what's relating in one of these objects and one of these kinds of theory and the various models that apply to it then become fungible. And then also that the apparatus for all the local is set up so that they have an analytical basis in analytical regions, and analytical character. Those are the ideas about this sensibility, then fungibility, and then that tractability ends up when there's a general means. For example, there's closed forms that says, well, I'll put above and about that, we've windowed this in and boxed this down, so it ends up becoming a square with a definition, and then in that sense it can be considered regular and ruleo in something like a perspective of and projective. That's how things end up becoming kind of altogether tractable for the analysis in the plane or these other regions. So that's been kind of interesting. And starting with that, then there was and reference back to the different methods and analysis from the nonlinear electromechanical effects and applications. So that was really useful to just kind of learn about developments in the field and beyond the usual linear in the systems of differential equations. And for usual differential equations, and about how so many of them in terms of the plane are defined in terms of the second order and the differential, because that's quite a thing. about the Laplacian and about how that's quite a thing for the gradient descent and the gradient in the planar. Then it was read into the introductions of these works about the differential geometry, about the methods of symmetries for the Lie algebras, as an example, and kind of like the Fourier analysis for these application of the writing of a function as an infinite series of orthogonal functions and coefficients about them, after establishing their convergence and existence, and after establishing then for various kinds of functions the convergence and existence, like a Fourier analysis. There's something like a Lie group analysis, which is it's going to have some similar kinds of aspects to it that it will make for that. You can find other interchangeable parts if they make guarantees, these derivations that establish for their properties, that for the integration under effect, in effect, in the model of area, in effect, and the areal, that for the definition of integration and the analytical character, that once it's established for these, like Fourier style, or for example Maclaurin style and Taylor style in power series, and those things which I need to learn more about, and the these Lie groups as an example in the differential methods, or for harmonic functions and some anharmonic functions, or what, coming into otherwise about the Laplacian, just as examples. The idea is to figure out for these classical approaches how to extract what are these parts that then make it so that it's well defined and understood what needs to go into supporting functions, or what are the fungible means in these analytical regions, like there's sine and cosine, and when they cross, and when sine goes to 0, it looks like it's d sine goes to 1, whereas or vice versa. That these are the kinds of things that are to get into what make then for having the analysis up above and separated from those, with the idea then that besides then, first of all, being able to plug that back in and getting back all the standard analysis, is after this deconstructive account, what goes into and went out of, having for the definition of calculus, which takes a long time to learn and to internalize, then that it can be kind of more briefly formalized, and the definitions of all these things for arithmetic and algebra and function theory and geometry and topology and operator calculus would each take all this time to internalize, and application that ends up being abstracted, and that then it becomes sensible to have it modularly fungible in terms of the interchangeable of what are functions or other or topologies, or whatever the various objects that fit into place that fulfill the thing, and then end up having things be tractable in terms of saying, I want to figure out the steepest descent or maximum ascent, or I want to find the principal components, for examples. That then it ends up to be about those kinds of things, when that otherwise it becomes possible to figure out, saying, oh, for some of these kinds of systems, when it's perfectly circular, or it is a straight line, that it's possible to drop in also placeholders for those that don't have to do anything to be straight, for algebraic geometry and geometric algebra. That for the algebraic geometry, really, the idea is to make sure that how it results is that there are adapters for either way, that when we're talking about real valued numbers, for example, and systems of real valued formulas, that they can be treated as such, and then besides that they do have what exists for them in the higher order, it doesn't take a higher order apparatus to make it fungible to deal with them. So then to get to some of the higher order results, like, well, in in algebraic geometry, some of this non-standard stuff would be after a 12-year course of studying algebraic geometry from these algebraic geometers from France if you wanted to have a chance to use their methods on their analysis. Well, no, the idea is to make a deconstructive account and then end up with, to have factor this mathematics, so that then it's possible to have it so that the extensions are direct, and besides that they're interchangeable and modular where it's apropos. And then that's to get into a lot of different things. For example, the treatment of the dynamics in models of objects of physics, where one does not need 26 dimensions to draw a straight line. Then the idea is that while it is so that those 26 dimensions are there for a reason in a particular model to show a particular thing in a particular sense of fungibility and tractability in all the things under interest and in effect, that the where those come and go together are to be kind of made modular in the interchangeability for the sensibility and fungibility and tractability of that. All the things are basically a dynamical modeling of a differential system parameterized by time. It's dynamical modeling. That really all the application of mathematics to real world things is this kind of thing. And so, are systems of objects governed by the laws of physics, say, is this kind of thing. And so that's kind of what's coming and going for it. Interchangeability and the notion of interchangeable parts was defined as one of the first things for the industrial age that became it possible to where things that were fine goods that were crafted were kind of crafted to piece, and then until then it became that there became like the interchangeable parts, and it was the assembly line of muskets or something. And that it ended up that after division of labor, where the person who ties the sheaves is expert at tying the sheaf, and the person who cuts the sheaf is expert at cutting the sheaf, or at least that's their mode. They don't get randomized by other work. That's their thing. So division of labor and specialization of labor, and then there's interchangeability of parts, and then there becomes like the assembly line, where the idea is that the work moves through the line instead of the line moving over the work. Tractability. These are just kind of examples to help describe then what's this factorizing exercise is for, is that currently and a lot of time, and anybody has this ability, that they can approach any kind of mathematical problem and frame it in their own theories, which start from the theories of like there's no attachment, it's just the inputs and outputs. The fungibility is traded for not having to care or not knowing how to care, and that's essentially like a weak side up to like a strong side. There's various ways to think of all kinds of ways that there are strong sides, and one is that, for example, it's like I have an empirical apparatus, and so I know what it is, or it ends up being a means of otherwise the empirical, and otherwise is for science and statistics, of course. Then the idea for this modeling, of course, for physics or mathematical science, is they end up then have these means and to figure out how things are sensible and fungible and tractable. Then that everybody basically recreates this whole kind of toolkit and tool set. So sometimes when we have to look at that and know that, like, well, you have to know Fourier analysis because you have to know differential analysis, and then you have to know differential analysis, and you have to know Liouville, or you have to know these linear systems, or you have to know all about eigenvalues and eigenproblems, or at least these few properties that are elementary about it that end up making it so that you can find some polynomials that you can crank those down to roots, and you can get some possible values might be solutions. Or these kinds of things that say, well, we got to solve all these integrals with calculus, and we got to solve all these integrals with calculus with trigonometry, or we got to find all these ways to arrive at this what is so and so is what in terms of these formulas or these models of action and inaction by these various models of wave motion, these kinds of things. there's a bunch of different little things that are expected to be known by everybody with the math degree that gets them to apply about what that's expected to be known about systems that model these physical systems. Again, it's not really my field, and so that's one reason I've been trying to study it a little bit, because when I want to know more about something like the continuum mechanics, like where Hermann Weyl is like, I need a critical examination of the foundation analysis. I kind of already have one of those, because I already have like 3 definitions of the completeness of the real numbers in continuity, like line continuity, field continuity, and signal continuity. So I have a lot to give what is dynamical modeling. And whereas dynamical modeling has that and calls what it calls that is the Jordan measure for this line drawing, or it calls it the path integral and the line integral, or it calls it infinitesimals, not standard, and they're not allowed. But at the same time, that it exactly is what it is. The calculus for hundreds of years is called the infinitesimal analysis. Then for the signal continuity, similarly for the Dirichlet problem, or anything that has to do with the topology, when two topologies meet and they basically reflect only when they're together that is continuous, but as they flex apart they are not, that the whole invariance about them, about conservation laws and symmetries and invariant theory only applies about that meeting, the signal continuity. These have been placed elementarily in the foundations of the objects of the mathematics under function theory and in topology, so that for all these definitions that arrive that for arithmetic and algebra of the objects, arithmetic of the numbers, algebra of the objects, about quantities, for function theory, how things relate, for topology, how continuous things relate, especially, and then for the operator calculus is above all that, when you can do anything to do with rank ordering or lowering, or projection and raising, or addition formula or index formula, or any way to relate two things in a set of numbers by another set of numbers. We call that operator calculus. About the operators and operations and that. All in terms of set or part theory, and then right above that is of type theories and category theories. Just all one theory. That this really gets into a lot of the things that have to go on then in terms of taking a deconstructive account of the standard formal basis for everything, because everybody's got to be able to prove what they say in mathematics. It's not always true that they care or that they do, because sometimes as long as the method is cranking out some numbers and they appear to be correct, they don't necessarily have the time nor the capacity to validate that what they have is formal. And there are lots of gotchas that have to do with anything from sampling theory and probability theory to the design of experiment, or anything to do with the numbers and all the assumptions that go into numbers, any of the mathematical paradoxes or logical paradoxes. Those all have to be got out the way to have for some formalist who's a rigorous formalist, that they want to be able to say that their mathematics is well defined and well behaved, and it's provably so. It's provably so. So most people, and of course pretty much everybody, has adopted the means of coming up with and being raised up with the whole curriculum as they are instructed in and exercise and internalize the curriculum, all the standard stuff, and here that's field continuity and usual arithmetic and usual algebra, and that it's elementary, and that the objects of it are atomic, and we don't get into quantities like they would be molecules, or we don't get into the non-standard because there's no infinity in these numbers yet, right? Because this way everybody can learn to build all the necessary stuff to get at least an analysis, and then we can build almost all the stuff. In fact, pretty much all the stuff is built in this at least leaning one side on delta-epsilonics. And so it's stood up this way. Now, without actually an infinity of the numbers and treatment and consideration thereof, it ends up being that at some point that becomes kind of like a house of cards, but it does stack up, it does stay fungible, and as well, where you can balance that and to make sure that it's closed and complete in all the assumptions and the elementary deconstructions and the pseudo and the quasi and the degenerate, that it becomes stronger. So anyways, everybody has the same linear curriculum built up of all these standard results, and then trying to figure out how to make that so that it's be provided an interface to higher level results in these resolves a lot of the factorizing of all these developments of these kinds of results. What results, ... is that's its own kind of exercise. A way to look at the numbers kind of holistically, all as a thing together as a part of monism and also for their own sake, but not uncritically, critically, that those are the kinds of things that are ongoing. So I started reading some few books which kind of branched into different subfields, and that got into symmetry, submersions, and sheaves. And really a lot of it then is about the submersions that I've been thinking about and working on, because the idea is that this identity dimension is this idea that you take x and y, and only take the positive numbers, and then x equals y is this identity function. It's a straight line, so if you think of that as the axis, then you can think of things that only exist on the line, like numbers, they just exist on that. And then in terms of functions of x and y, first of all, is that they cross this line, and so it's kind of like if you had two independent dimensions besides, if you had three dimensions, and they were coming across this line, they would be whatever they are in those dimensions that they have. They just happen to have coordinates, and then they would just translate whatever they are to these coordinates in this identity dimension, or at least its values first, and then about the conformal mapping, or the mapping between the octants and the quadrant and the planar. Then there's also the things that are kind of made for extensions in the analytic continuation. Like, well, after we have the whole the whole line of real numbers, we just go up to the complex plane and make a Gaussian analysis to get analytic continuation in this stuff like zeta and these things, or z, the argument z complex, because there's roots that exist in it, and there's an arithmetic and an algebra, and it maintains and carries some products and makes some things fungible that has been built out, how then some such of those things are tractable. Well, the idea here is to figure out what is kind of just some limited subset of these things to make it so there's some bases and kernels of what are some of the origins of the things that then for this what's singular in some of these differential systems and equations, like the linear fractional equation, Claros, and D'Alembert's to begin, because those are some of the most well-studied of the differential equations things, because they're just applying arithmetic and algebra to the differential quantities, with the idea of being able to treat the differential and integral quantities as under operators just by their order, and especially when they establish and maintain linear relationships like the exponential does in the differential, ... That the idea is then with this identity dimension, it's about just trying to reduce kind of first just to this xy plane, and then about only these positive numbered things, and then just about kind of just a sandbox of sorts, a playground, where then what results from two different perspectives, both drawing functions in the xy plane and seeing what they mean in terms of this identity dimension and how it's kind of singular to it, and drawing functions in the octants with considering those to be their own quadrants. Like between x equals 0, or excuse me, between x equals 0 and x equals y, or between y equals 0 and y equals x. So these two octants, besides considering those as what we were just talking about, having that symmetric about those, whatever you draw in terms of x and y, is drawing formulas as they would be in the xy octant as transformed in coordinates into those, so that for the polar notation of just radius and angle, meaning we have an xy plane, and you just mark out the radius, and then you compute for that line that connects the origin to the end of that radius by the angle theta. That's the point that's the unique and distinct coordinate in the radial and angular, that point. So if you just multiply the angle by 2, then that fills the whole octant. And so then the idea is to figure out these kinds of things, and to make what's fungible in what's this differential geometry, as it's called, some of these submersion, lowering the rank, and then finding what can be built up from that as elementary, was then going to make some elementary things which would look like what would happen from a higher dimension, again coming back and forth and going back and forth from it. That it builds for a singular a place for it to branch from. Once you introduce the negative numbers, then they happen to be that there's, for even functions, that they're roots of positive numbers, and for odd functions, they're roots in the negative numbers, but for even functions, that they're roots of positive numbers. And similarly for the complex numbers, then we're going to go and extend that outwards and have the roots of unity, the infinite roots of unity, now live in this complex circle. The idea is to figure out how this infinite roots of identity is make for this infinite roots of 0. This sort of original analysis that's going to arrive at, for basically starting with the reciprocal, the inverse, aka the hyperbola, which is the shape that is drawn for the hyperbola, 1 over x, y equals 1 over x, or x equals 1 over y, or 1 over xy equals 1. That's going to arrange that for this xy equals x squared and xy equals y squared, of the identity function that 1 over xy or 1 over x squared or 1 over y squared equals 1. That these are the kinds of things going back then for the root of unity to help explain what these attachments mean. And I've just kind of invented this. I'm not really sure if I've ever seen something like that before, or if it's just kind of seemed to fit, because what it does is seems to fit is where division by 0 fits. Division by 0 would be like multiplying by infinity. So it's called singular. It's undefined and usual naive arithmetic. where usual naive arithmetic is addition and subtraction and multiplication and division in real numbers. But really that is increment of integers and addition to integers and multiplication integers and tetration integers and building all these powers in the modular in addition. So then similarly you could say that for division. Say, well, I can only have, if you only can have two operations of arithmetic, what would they be? Well, one idea is like, well, I want addition and then I want subtraction so I can figure stuff out. Or I want addition and then I want multiplication so that I can parallelize things that I can figure out this way. Or, you know, I want multiplication and subtraction because, well, I'll think about it in those terms, whatever. But what if it's the kind of addition and division is kind of like, well, I can divide stuff or I can multiply stuff by addition. And so, and then it's like, well, it's a little bit extra work in having to do multiplication by addition, but it's a little bit less work having to do division because it's its own proper thing. Because everybody knows that the hardest thing to learn in 4th and 5th grade is long division, because it's the first mathematical algorithm that involves placement and carriage and in multiple graphical directions. That's the thing. So anyways, here then with regards to about division by zero not being defined is that, well, in things like the linear fractional equation, exactly this identity dimension is the first thing that's undefined. Oh, really? Well, yeah. And so it's singular, but everything that you still have to imagine everything comes and goes to it. Because just like division by zero is undefined, you know, if you divide thing by a larger and larger and larger number, it goes to zero. And so the reciprocal of that is, you know, like so. And that the completion of it arrives at that's the singularity, the asymptote, the vertical, the asymptotic and the vertical. For our linear and what is all parallel, linear, and horizontal. In projection and perspective and all this usual geometrical stuff that's correct and great and maintains form and proportion. Well, no, anyways, I'm just kind of attaching some allegory to it, but I've been attaching some application to it and making some figuring about how about folding up the xy plane in the positive and negative numbers, the xy plane with the origin in the middle, planar, and for all planar functions and planar surfaces, into this quarter of it, and then to get figured out what ways that I've long ago forgotten, because this was, you know, the elementary introduction to methods of graphing functions and anything to do with the mental model of the objects of arithmetic, correspondingly later the objects of algebra according to the functions and their graphs, or charts, if graphs is already a thing and a different thing. These are the kinds of things going on with it. So I haven't been much consulting, you know, one of these textbooks, any of which is really quite great. You know, I haven't found but only a very few, if any, yet typographical errors, or and not found anything really to argue against. You know, they're careful in their words and not incorrect. They're not necessarily complete. There's a difference between correctness and rigor, and then vis-a-vis what's in the wider sense complete. That's fine. I don't expect them to be because it's standard, and they would have to build from the title of the book would have to be, you know, Axiomalist natural geometry or something like that to arrive at all these things, with 3 definitions of continuity. But now I'm curious if I can read something about this, because I'm pretty sure that this identity dimension would be related to methods of symmetries, and it's related to methods of sheaves because it's topological about when it is a continuous domain and when it is so versus the two dimensions that comprise it, or conversely, the two dimensions that it lags or carries their square, and this kind of thing. Making up some new words, but usually avoiding inventing new words whenever possible, but filling out the spaces of the existing words as much as possible. Then now I'll be rereading some of the beginning of this differential geometry, which is lectures given on the topic of differential geometry, to see if I can read into it some more of the context about sense analysis. Differential geometry was just introduced in the following chapters, also referred to as Euclidean differential geometry, is based on Euclidean space, e to the n, as the ambient space. So Euclidean space is defined as a space that's bounded above by this by its dimension, and when for e squared it's got points and lines, and for e cubed it's got points, lines, and planes, and everything else is just built of those. So there's no real space except that about the functions that define in terms of the collinearity of points, because the space is not an object in Euclidean geometry. There's only a collection of fundamental theorems. The Cartesian space fixes an origin, and otherwise it's the same, because it does though have real value variables as the non-integer part of what is an integer lattice. So it's got an implicit integer lattice for the Cartesian, because a vector space, like in two dimensions, can be defined in terms of that. So here, in terms of this identity space, it's a space in its own dimension, of course, because that's just got an identity vector, and then it's only scalar products of that. It's just a line or array. It does not necessarily need. Oh, I suppose, does it need inverses? I don't seem to recall that a vector space needs inverses. In which case, it would be some kind of half inverse space, or it would be so until it's defined down to zero, or it would have to be kind of a magnitude modular operation to make it so that the whatever's the product that is the vector space addition would have to come back to zero, and so that's just about that. Then in a vector space, all the theorems about objects of a vector space can be applied. In the Euclidean space, all the theorems about objects in the Euclidean space that are Euclidean constructions can be applied. So he says, the most important algebraic structures on this space are, on the one hand, the structure of the vector space, and on the other hand, the Euclidean inner product. It's usually the scalar product, dot product. It's readily and easily computed. It's a scalar. It's used in many formulas to indicate where it's on the left or right or something, or above and below. It's used to compute the norm, the distance in the metric. In addition, we use the topological structure in the form of limits, open sets, differentiation, and integration. So he's saying that he's using the standard open topology. There are others, this is an example where it's correct what he says, but there are others that he just does not mention at all. So as long as it does not mention it at all, then they don't exist. They do is they can be attached to the same things, but it's the responsibility of the person who does that to attach all their own correctness about all the bridge results, these ponds, the bridges between this and that, so it's correct. Differentiation and integration. By fixing a preferred point as the origin, one can identify Euclidean space e to the n with r to the n. They're real numbers. The integers are usually called z for Zahlen. It's a German word for numbers, and r for real, and it's a German word for real numbers, and then c for complex, which is Latin, I suppose, which will be done implicitly in this book. For basic notions from linear algebra, he refers to another book, and for the basic notions of analysis, including ordinary differential equations, he refers to another book. And then this chapter is only meant as a list of some basic notions. This section will be used throughout this book. The implicit function theorem is useful but not absolutely necessary, and the notion of a submanifold is helpful but not really a necessary prerequisite. Therefore, the reader may skip directly from sections 1.1-1.3 to chapter 2. So as this is building stuff up about the members of elements of vector space, what I'd want to do is figure out what that means for the identity dimension. My idea is to stake out everything that has to do with the whole space with just a subset of the space, this submanifold. It's also a submanifold, I suppose. And about what it means to make it so that either things are defined for it that reflect how it comes in down into it, or there's made an adapter for that anything that's implemented above is implemented in terms of it, and it projects out. One or the other has to be kind of put into place to make it so that then it fits. Then it can apply all the same things to this and that, as that to this, and then anything that serves as one of these objects in these higher level constructions, like R2, R squared, has this analog or multiple models and various ways to look at it in this identity dimension and its spaces. So he talks about a vector space with an inner product, scalar multiplication, it's a vector space. For two vectors x and y, that the sum of their coefficients in each dimension is called their inner product, but that's not necessarily what I still have in mind. Distributivity, the various properties of associativity, commutativity, transitivity, distributivity really go a long way to affect and defining these things. But then also he emphasizes symmetry, bilinearity, and positive definiteness. Where positive definiteness is a property as of that the inner product of x and x times itself is greater than 0. So it's kind of like this is an even function in the sense that when you put these two quantities together, that it results in positive. That then is a property of this product, so that it carries all the products in this space. And so it'd be similar for anything that's positive definite and carries it back to the xy. And so it'd be similar to establishing for these properties symmetry and bilinearity and positive definiteness is the same as be so for this identity dimension. So then bilinearity is that a scalar times x plus a2 times x. So the sum of two scaled quantities distributes out this a1 times the inner product of x1y and a2 times the inner product of x2y. Well, that seems to make sense how that would be the same, because as long as there's maintain a coordinate basis and setting, then whatever still holds true for all the things that are only in the first quadrant, because it's positive definite by default. Then whether it lands on this identity dimension is kind of where it wouldn't be in terms of the view, the skew view, or the view. The metric distance between 2 points x, y is then defined as the norm of the difference vector y minus x. See, this happens to where if otherwise it can be something that is so defined and made up so that as long as it maintains the metric and the norm, it doesn't necessarily have to be the same thing. For example, where y minus x equals 0 on the dimension vector, that basically is like, well, how far is it distant from the additive identity? It's 0. This makes R to the n a normed vector space on the one hand and a metric space on the other. Euclidean geometry can then be based on these notions of lengths and angles in conformal mapping. So then he talks about R to n is a topological space. The topology of R to the n is strongly based on the notion of an open epsilon neighborhood of a point x. And it is. We talk about the critical points, which is where a critical point has, in every neighborhood, it's got a dense region about it in every neighborhood. And then there's always, pretty much always the open topology, but there are others. And for example, it's kind of an anti-open topology. Of a neighborhood of a point x, u sub epsilon x equals y and r, given that the norm of x minus y is less than epsilon. So, with the help of these neighborhoods, the notion of convergence and of the limit of a function are defined. And here we want to get above that, so for this completeness, and then for the limit of function, and then limit of a limit of functions in that convergence. Moreover, a subset O is said to be open if for every point x in O there is a certain epsilon neighborhood U sub epsilon contained in O for an appropriately chosen epsilon greater than 0 depending on z. Every point in the open subset. Then the topology of R to the n is defined as the system of all open sets, including the empty set. Closed is if its complement is open. So yeah, figuring out that anti-open topology is something that I really need to spend some time on. Because when I sat the topology course for a mathematics degree, it was a class all itself, and so every week or so it would have a given development of a derivation that was walked through, and kind of everybody sat through it and saw it as so, and developed all these things to do with the definitions of the terms and the functions and the formulas for the topology class and topology. And when it got to one point about it, and it made a result about the rationals, and so it was, and then it was kind of basically contrived like this, and this result in topology agrees with the facts that the rationals are countable, and that the irrationals are uncountable. And it's so, according to set theory, there's a model of the real numbers where the rationals are countable and the irrationals are uncountable. And that's field continuities, and it's standard, and it's great. So anyways, though, then we talk about counterexamples in topology. And it's like, there's a book called Counterexamples in Topology. And one of the first things that I remember finding a copy of this book, because I was really curious, I want to know about counterexamples. and in topology. And one of the first ones is like, there's no smallest positive number. All right, but it's a counterexample. So, anyways, for this theorem about the rationals, I pointed out that it was really true for a set of objects in their reals that are dense in their reals, like the irrationals, so that the rationals would fulfill the same. But that would get into, that would have to make the whole development stood up to that point to keep it from tipping over the other way or falling over the house of cards. So it's a thing. Well, that's kind of what we're getting into here. Then he gets into differentiation in Rn, and he says the most important notion for the contents of this book, Kuhnel says, is that of derivative or differentiation of real value functions, which are defined on some open set, or more generally, of maps defined on open sets. So he makes a pretty strong emphasis on that, because really what it means is that they're compatible without having to deal with otherwise considerations of their compatibility and differentiability in terms of making later that they're going to be submersions and immersions, because then he gets into his submanifolds and the main definitions he makes for his own opinions about that the curve different derivative is not zero, that this is the thing. And he says it's differentiable. There's a linear map from Rn to Rm such that in the neighborhood U sub epsilon x, one has the neighborhood in this point is small, and it's on the order of epsilon. Here the symbol on the order of the norm of epsilon means that the terms indicated by it tend to zero as epsilon goes to zero even after previous division by it. Then it's the linear map described by the Jacobi matrix or the Jacobian. The rank of the map is a point, then it's defined. It's the rank of the Jacobian for purposes, his differential geometry purposes, where he's going to make things really fungible in a lot of these in a lot of these systems to make them tractable later, and just to make things quite tractable, is at the cost of this opinions about what can and can't be done and how and why is so, that then it would have to admit or deny to an analysis that's deconstructive about the interchangeable, whether or not there exists a bridge from it back into the greater analysis. In this case, one calls the map F an immersion in the case that the ranks one is lower than the other, or submersion in the case that the ranks one is higher than the other. An immersion, respectively submersion, is characterized by the fact that the Jacobian represents an injective, respectively surjective, linear mapping, the linearization of F. The importance of this property becomes quite clear in the implicit function theorem. And so, yeah, that gets into the linearization, and that linearization is basically the word for approximations, or what that it so happens that for many linear systems, that's still that the error term is on the order of zero, and that's kind of seems to be his definition, that this linear mapping exists, that the difference from it is about zero. So as long as you can establish that, then you can kind of write it this way, and it's kind of a nice form because it's like so. Well, that's pretty great. And so that's what we got to then. That what I'm interested in, though, for the identity dimension is kind of the opposite of that, because I want to have the linear components and the circular components kind of reflected in this together, and about how it's going to be that 1 over xyz is this hyperbolic 1 over xyz equals 1. what that means with respect to x, y, z equals 1. And that being about 1 over x equals y, and 1 over y equals z, and 1 over z equals x, and 1 over x, y, z equals 1. The hyperboloid and the boloid, I suppose. There's that kind of thing, and then otherwise for this identity dimension, the idea is that besides that it's possible to figure out some linearizations about it because it's singular, and so it's just kind of going to be there about then a bunch of different things. I'm looking to attach to it all kinds of different hangers on to figure out what ways that make for projection and perspective that becomes tractable for things. That it becomes fungible for things, and then that becomes very tractable for things. All right, then, hey, have a great day. Solve the multi-body system. Have a great day.